Good morning. Hello. It's great that you guys are such good friends. All right, so we're going to cover some of the more other statistical tests and different terms, ways to describe our data. So what are some of the ways that we've talked so far about how to describe the data? So if you got a data set and you're trying to tell somebody about it, what are some of the terms that you're going to use? We call them figures of merit. So numbers that represent the data. Because if you have 100 data points, you can't go through every one of them. You want to give a single number or a couple of numbers to describe the data set. What would you use? It's not a trick question. It's pretty easy.
You randomly chosen data points?
You could do that. You could maybe pick like the high, or maybe not random, maybe the high, maybe the low. So you can get the range. What's another one? The mean, exactly. Average, what's the average? The central tendency, they say. The median, which is the middle data point. So we'll see today how the mean and the median can be different. What is another one? Range, we did that, yeah. This one took you a while to calculate when you were doing the measurement exercise. Exactly, standard deviation. Okay, so today we're going to look at a couple of other terms, the normality test, skewness, and kurtosis. So we're going to try to describe the shape of the distribution. The mean and the standard deviation are typically representing, well, they best represent the data when the data is normally distributed. So you have a mean and you have a normal scatter around that mean to form a bell curve. You kind of see that normal distribution bell curve. Today we're going to look at data that does not fit the bell curve. Okay. So here's using Minitab. This was the analysis of the trainee data. And this is called a histogram. So this is another term that you need to know. This type of plot is a histogram. And these blocks here, right here, this is called a bin. And can you tell by looking at this what our bin size is? Like what's the range of numbers for each bin? So here we have a 12 here, and we have a 13 there. So this one is probably, what, 12 and a half, right? So it looks like our bin size is 0.5. Okay. So they've divided the sort of data range into 0.5 bins, and then in each bin, how many data points fit into that bin? So let's see, how many data points do we have in this one? 10. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so all of the data points are here. This is divided here. This y-axis is not shown on the Minitab plot, but this is called the frequency. And is the y-axis. And it's not a frequency like you think of in terms of CHEM, right? It's not like cycles per second or hertz or anything. It's just a count. It's how many items are in each bin. So if you look at this, we have 10 total data points, and we have 1 here, 2 there, and up here is 3, right? And so in the bin between 12.25 and 12.75, we have 3 data points. And so there's a frequency of 3 in that bin, and there's a frequency of 3 in this bin. But in this bin, there's only 1. And in these 2 bins, there's 0. And then there's 1 in this bin up here at 15. Okay. Does everybody understand the frequency axis and then the bins? So you're just dividing the x-axis into bins, and you're counting how many are in each bucket. That's a histogram. Now this down here is a box and whiskers plot, and it shows an outlier. So it's showing that this number, this 15. Remember, these were the cocaine measurements, and so the trainee had one at 15, and then had a bunch down here close to the true value of 13.2. This is their box and whiskers plot, and it says that that's That's an outlier at 95% confidence. This is the mean plus or minus the 95% confidence intervals. So it goes up above 13.5 and down below like 12, 12 and a quarter. And our true value was 13.2. So we don't have that in Minitab, but our true value was 13.2. Now this blue curve is the Gaussian normal distribution. And if the histogram matches the normal distribution, then your data is normally distributed. We have an outlier here, so there's one point that doesn't quite fit that, but does the rest fit the normal distribution? Well, we'll see. This is the probability. It's the p-value. Normally distributed. I'm running out of space. Okay. And then we have some of these other terms here that we're going to get into. We have the skewness and kurtosis. So we're going to learn about those today. Any questions on this data representation? This is super easy to do in a stat package like Minitab. That's why if you're going to be doing statistics in the future, you want to get a statistics program. You can do this whole thing in Excel, and we'll do some of the plots if there's time today in Excel. We'll do a histogram in Excel, but it's so much easier for something like Minitab. You just have the data in a column and you say, give me the graphical summary for this data. One shot, gives you everything. So that's really nice, especially if it's part of your job. You want to do this over and over again. It's really nice to have a menu item that gives you this whole plot. Okay, so here's how you do it in Minitab. You have your data columns over here, and you just go to the graph and graphical summary. If you're in Minitab, which again, you can get a free trial version if you want to try this out for like 90 days, which would last the semester. So if you want to explore Minitab, I encourage you to do that. And so I have a couple of places in the notes occasionally like this that teach you how to do things. Now, anytime you see a p-value, I told you what that p-value was, but let's say you didn't know and you saw a p-value. Here's a probability. You're like, what on earth am I going to do with this p-value? I don't know the null hypothesis, right? And so you can come up here. Minitab has a really good help menu and a really good stat guide. So you can go to that stat guide and you can pull up the statistical. It's like a textbook, a stats textbook inside Minitab. And so if you don't understand something in Minitab or in Excel, use the help menu. Excel's help is pretty good. It's not like the old days when you would hit help and it would just basically tell you how to save a file and how to close a file, something that you already knew, and it wouldn't tell you the thing you're looking for. No, the help in Excel and in Minitab has gotten better. And they're starting to use, Microsoft is doing this with the Bing search. They're starting to use AI to search through all of their help files and kind of have a conversational help. So I just recently ran across this a couple of weeks ago. Man, it was great. Went to Bing because I heard they had this AI thing, and I asked for help in some Microsoft thing, and I got a conversation, and it said, yeah, to do this, you want to do this, this, and this. Does this help? And I was like, well, I'm really more interested in such and such. And then it goes and analyzes some more. And so it was amazing. Yeah. And it cited its sources so you could click through and go see the original article. So help is improving. That's wonderful. And so if you go to that stat guide, here's the information on the Anderson-Darling normality test. The null hypothesis, this is the data, follows a normal distribution, and the p-value is the probability that that's true. So if the probability is less than 0.05, then we would reject the null hypothesis. And so for our data for that trainee, the p-value was 0.9196. So it was about a 20% chance that that data was normally distributed. So that's that, you know, we would accept that null hypothesis or fail to reject it. You can compute it for other distributions too, but you know, we're using it for the normality, the normal distribution by default. Okay, now let's look at the forensic chemist. So here's the histogram for the forensic chemist. Again, on the frequency axis, we can kind of look at this. We know we have 10 data points, so we can find out which ones there are. I'm just drawing these lines here to show you the frequency axis. So we've got 1, 2, 3, and 4. You couldn't do this for a lot of data, but I just am showing it because we only have 10 data points, and so you can kind of figure out what the frequency numbers are. So is this data, again, the black or the gray squares or columns, that's the histogram. Is this normally distributed? I see people immediately shake their heads. How did you know so fast?
It's skewed to the left more than the right.
Yeah, so we're looking at this. Okay, so left versus right, we'll talk about that. Yeah, it's skewed to the right in this case. The tail is where the skew goes, okay? What's another, so that's a qualitative description. You're looking at it and saying it doesn't quite match the blue curve. The data is more weighted on the left, and it's got a tail that goes to the right. But those are qualitative descriptions. Is there a numerical description of whether the data is normally distributed or not? The p-value, yeah, this normality test is 0.017, okay, and it's less than 0.05. So we would say this data is not normally distributed. That's just a qualitative measure. It's not saying the data is bad, okay, but it is saying that if you're going to use your standard deviations and your 95% confidence intervals and so on, those are based on, especially the confidence intervals, those are based upon normally distributed data, and your data is not normally distributed. So that's just a little warning flag to say, okay, the use of my 95% confidence intervals has a, what my old advisor would say, it's got a dead body buried in there, right? You're using your 95% confidence intervals, but it's not normally distributed, right? So that's a little bit of a mismatch. It's not critical, but you just need to be aware of that. Okay. And then this skewness. This skewness is a positive number. And so we'll discuss what skew is, positive. So this means it, and I use the word tail. Tails high. So how do we describe it? I'm going to draw, I don't know, what kind of animal has a long tail? Dinosaur. Okay, very good. So we've got this, very good. Okay, so we've got big old haunches here. All right, little arms. Yeah, big old mouth. His mouth is wide open. And his tail goes like that. Okay, so that's my T-Rex. Here's his eyes and here's his teeth.
Horrifying.
Yes, exactly. Yeah. Okay, good. All right, so that's the tail of the skew, and it goes down like a tail. That's really good, actually. Anyway, and so this, and if it's positive, that means it's tailing, and right or left it can be misleading. In this case, it's right, but we want to look at the which is the high numbers. And so the positive means it's tailing towards the high numbers. We could have plotted this in reverse order for whatever reason, and it would tail towards the bigger numbers. So right or left may be misleading if the numbers are plotted in the opposite direction. Okay, so that's the skewness value. Anything else? Okay, so then here's kurtosis. Okay. This is an interesting one. You could potentially describe this with two distributions. So we're always worried about our data being, not represented by a single distribution. So what would be an example of two distributions? Well, in this case, you might have a distribution that looks like this with a mean and a standard deviation, okay, and a distribution that looks like this, that's really narrow. So this would be mu1, this would be mu2, and this would be sigma 2. So sigma 1, sigma 2. Do you see how that could be two distributions? But they all have very similar mean. So this would be as an example where it's multimodal data, meaning you have two different distributions, but the means are really close. It's the standard deviations that differ. Okay. The previous one, it had a small kurtosis value, but it could also be, two distributions. It could have been one down here and then a really broad one spread out like that. So kurtosis is sort of trying to detect when you have two distributions or many distributions that are not fully resolved. Okay, so let's look at those in closer detail. We'll go to the Minitab stat guide. Okay, and this is the information from the stat guide in Minitab. So kurtosis is the degree to which the data is peaked. So data that followed a normal distribution would have a kurtosis value of 0. Okay, 0. So that's what you're aiming for, 0 kurtosis. A distribution with a sharper than normal peak would have a positive kurtosis value. And you can kind of see what I drew with the one. This might be two distributions. It might have a wide distribution and a skinny distribution on top of each other. And they have the same mean, but very different standard deviations. Okay. I've been thinking about grades a lot. I'm a professor, right? So I deal with grades all the time. And so I don't know that you could detect this, but you might, let's say you have a group of students that have a copy of the test. So you got 5 students that have a copy of the test, but it's an old test, and I've changed, say, 20% of the problems, okay? So that means 80% of the problems are exactly the same as that old test. And so these students go in and they're like, tick, 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 and all of them get an 80. Well, I mean, one 82, a 78, but it's centered on the 80. That's the real narrow distribution, right? And the broad distribution is all the other students that didn't have this copy of the test. See how you can get the same mean, but a wider distribution for the students who hadn't had the copy of the previous test. They get, up to 90 and down to 60 and so on. And so you get a broad distribution, but then there's something unique about a small group that's really narrow distribution. And so that would be an example where you might get really peaked data right there. Now, whether they would all have the same means, I mean, who knows? But my point is, there's something different about that group. And so we see that here. There's something different about this middle group versus the rest of the group. Okay. Now this one, flat peaked. It's kind of difficult to get a really flat one, but you have nothing out here on the wings, and then you've got a bunch like this square distribution. What could cause that? Well, you might have just some overlapped groups that aren't resolved with narrow distributions. So because it's a narrow distribution, meaning there's very if you have a standard deviation that's close to your mean, a small standard deviation, it's going to fall off real fast. And so when you get higher than this top mean, it's going to drop off real fast. And it's dropping off on the low side too, but when it's dropping off, the other distribution's coming on. And then it drops off, and then the third distribution's coming on, and then that third distribution drops off suddenly. and then you have nothing out in the wings. That's not a normally distributed thing. So this is telling you there's something funny going on with your data. You have a negative kurtosis value, which means the steepness of your wings is too steep. Something's going on there. So hopefully you understand kurtosis now. Okay, and then skewness, we'll go in and we'll look into that. Here's the mini tab. You can see this skewness is smaller than this one. So this is how much it tails. So this one doesn't tail very much. This one tails quite a bit. And just remember the dinosaur. And so here's the skewness value, positive, and they use right, but I'm going to say high. Okay. And again, the assumption is that your data is plotted from low to high values, left to right. But I want to try to break you of that in case you get data that's scaled the other way, or written the other way. And then negative is left or low skewed. Let me get this door. Okay. So we can look at a couple of examples of skewed data. This says salary data is often skewed in this manner. Okay, and so let's look at some of those. Here's the salary data, and this is a histogram, and you can see the bins down here. So this is saying that categories are in $5,000 increments. This is for annual household income, 2010. And so under 5,000, let's see, this we have 3.5% of households. This right here, 15,000 to 20,000, or 19,999. This is called the mode. The highest value in a histogram, the tallest frequency, that's the mode of the distribution. And then the median is the middle value. So if you were to rank all of these incomes from low to high, and you go right to the middle one, that's the median. It's not the mean. Okay, it's the median. So this is the median. And the mean is not shown on here. I don't see it. Okay, this is saying that this is the 75th percentile. 75th. It looks like 25. Let me get that. Okay, so right there is the 75th percentile. So somewhere in here is the mean. Okay, we'll just say that the mean is right here. And the average in skewed data is always misleading to some degree. Okay. And also, so this is so skewed that to count, these, to just sort of keep these going out with the regular old bin of $5,000 would stretch this chart out so far to the right. Like, over here it's 250,000 and over. That's like a catch-all bin. But if you were to buy $5,000 increments, you might have some here, some here, some here. This chart would be so wide it would be ridiculous. And so what they do is they have an over bin. So 250,000 and over is everything in that bin. And that just helps bring the chart into a manageable width. So that's what's going on with that. They also have a bigger gap here. They go from $5,000 bins to a $50,000 bin, 50K bin. And then this is called an overflow bin. So it catches everything that's greater than that top number. Okay. Now, when would this come into play for you guys? Y'all are about to go search for jobs. Yes, maybe some of you already have some lined up. That's great. But whenever you're looking for jobs and they quote in a region the median salary or the mean salary and so on, always go for the median because it's more representative of the likely salary you're going to get, or the likely salary in that region. Because here's the mean, and let's say the mean tells you $70,000, but the median is $50,000. Right? Big difference between mean and median. And so salaries are always skewed that way. You're reading a news report and they're reporting mean salaries or average salaries. They're doing that for a reason, because that's not representing salary data. The median is better representative of salary data. So always read with a critical eye. Like whenever someone talks about a percentage, ask what the absolute value is. Whenever someone's talking about the absolute value, talk about the percentage. Ask about that, because they're choosing between those. And that's one of the most common ways to manipulate information to somebody, And so let's say you want to talk about you're in charge of an organization and you are short, say, $15,000, okay, in hitting your target. That sounds like a lot of money, okay? But if your budget is $100,000, you're only down 15%. 15% doesn't sound as big a deal as $15,000, right? And so you're choosing one or the other if you're trying to present the data. And so it's always good to ask, well, what is the actual value, not just the percent, or what is the percent if you're given the actual value? Okay, so that's a way to sort of listen critically. Any questions on the histogram? The mode is even better. So that's like the most frequent one. And in this case, the mode is 15,000 to 20,000. That's really, really low. Yeah. Okay, age of death is a negative skew. Okay, so this is the distribution of age at time of death from the Social Security Administration. There's a statistical difference between male and female. We have an overflow bin down here. Okay. Well, do it? No, it's not an overflow bin. That's just infant mortality there. Yeah. Yeah, so, if you make it through your first few months, you got a really good chance, right? They have the APGAR scores and all those things, the baby, heart working fine, all the different things. But then you see how much it drops off once you get past those first critical moments. And it's really small, deaths per 100,000. So really low number there. Then you have the male teenage years and early college years. This is why your insurance is more expensive when you're driving. Okay. There's something else that happens here in 55, 60, so I need to pay attention to that one, right? So this has got me distressed. These are my little glasses. I'm looking at that with an exclamation point. And, and so then you get out here and, this is a significant difference. Now, I mean, there's a huge amount of overlap. So yeah, our mortality is pretty similar, but this is a 5 to 100. So that width is about 5 years right there. So you say, well, that 5 years on 100,000, that's only 5%. 5% doesn't sound significant until you're 95 and you're like, oh man, I want 5 more years, or maybe you don't. I don't know. 95. Yeah. Again, average, mean, or median would make a difference here. You would want to look at the median. The median is going to be closer to the top. The mean would be down here. And then these maximum values are the modes. The most frequent. and this is tailing left or tailing to low values, and so it has a negative skew. Now, the symmetry of the data, you could have a zero skew and still have some really strange data. This is a classic example of bimodal data. Remember, the mode is that maximum value. And this is bimodal. It's got two modes. Okay. I'm trying to think of what would happen and what could possibly give me this kind of data. Let's say that, again, taking the grade example, let's say I'm a real jerk professor and I'm pissed off at my students and I make an impossible test. And so a bunch of the students make 0, okay? And a few people get lucky and get 10% or so. And then, but this group stole the test. They snuck into my office and stole the test, right? So you got some hundreds and some zeros and nothing in between, okay? So it could happen, right? So that's an example where you know it all, or you know nothing, and a very little in between. So that'd be an example of bimodal data. Okay, here's bimodal data, and that's a problem with bimodal data because the mean and the median are misleading for the whole distribution. So in this particular case, the mean and the median would be right here, you know, mu, and we don't really have a letter for the median, but you know, what do we typically assume when we're given an average? That's where most of the data is going to show up, right? A normally distributed data set, the average is right in the middle of the bell curve, and so that's where most of the results would be. You see how this would be a problem? If you give me the mean, and I'm thinking the Gaussian curve, the bell curve, and this is what your data really looks like, that's not the most probable result. The most probable result is above or below that mean, not at the mean. Okay. So this can be a problem. Okay, so we have some other analyses that we can do on that trainee data and the forensic chemist data. So this is what's called a process capability. Now, I'm not so sure, but I think it's probably moving in that direction. This is what we would call that 6 Sigma quality program. I'll say it's big in automotive. Okay. Chrysler, Ford, Toyota, those were the big ones that implemented this decades ago. Again, their goal is to have less than 3.4 defects per million opportunities on their vehicles. It's a great quality program, focusing on what your capabilities are. Okay. If we were to take that kind of attitude towards the forensics lab, okay, then we would look and see what our lower specification limits are. So let's just say, again, let's just say we analyzed this data. It was at 3.2%, 13.2% cocaine was the sample that this trainee analyzed. But let's say if it were below 10%, we had a reduced charge. Now we know the true value is above that 10%, so they should get a higher charge on this. But the lower specification limit was 10%, okay? How many of the trainees' analyses, if given a sample of 13.2%, how many of those would be incorrectly labeled less than 10? You see what the question is. We give them 13.2, which is definitely above 10. They analyze it, and with their standard deviation, their precision, they incorrectly report it as less than 10%. So we're trying to figure out what the area under this little curve is that goes down below the 10%. You see, that's different than a 95% confidence interval. This is saying, here's our specification limit. How many times are you going to be wrong in this analysis? And in this case, out of 1 million tests, 972 would be below, incorrectly below that specification limit, or a false negative rate of 0.09%. Okay. So about 9 times out of 10,000. I mean, it's not huge, but it's not nothing. Okay, and you don't want them having incorrect results like this. Again, this is a sort of a canned analysis out of Minitab. You give it the data, you give it its specification limit, and say, give me the process capability, and it will tell you what your process capability is. Here's the forensic chemist. Okay. Same target, 13.2, they analyzed it. Remember, their precision was much tighter. And so that because their standard deviation was so small, look, their curve drops to 0, and down here's the 10% false negative. And so it's listed as 0 times out of 1 million, right? But we know if it's only giving us 2 decimal places. So we can say that it's less than 0.005 parts per million. So out of 1 million times, they would not be falsely reporting below 10. Now, what would be an acceptable rate? When, if you say, less than 1%, you could scoot this down until that area is say, less than 1%. If their data was down here, so they could get down to say 11 or maybe 10.5 and still have less than 1% false negatives. So this is a way to kind of set their administrative minimums. You say, well, we're going to analyze this sample. The forensic chemist gets 11%. They're like, ooh, we're getting close to my 1% false negative rate. Okay, so let's do a second analysis with another technique and see. Okay. But if it's 13%, no, there's no chance that this is less than 10. So you can go ahead and provide evidence that this second charge should apply. That is more than 10%. So that's a capability analysis for a forensic chemist. We did similar, and this is that data that I did with the contact angle. Again, not very skewed, not much kurtosis here. So it's 0.5 skewness, 0.4 kurtosis. Very, normally distributed, 81% chance this is normally distributed. Look at the histogram and the blue curve, right? It looks very similar. Okay. Then we get it dirty. We put a bunch of grease on there. This is a slight negative skew. You see here this minus sign and almost 0 kurtosis. So it's not super peaked. We do have this peak here, but it's apparently the numbers work out to where it's not a lot. Okay. So slightly negatively skewed, which means it's skewed towards low numbers. We wiped off all of that gross contamination, and then our data became very narrow. 73% chance that it's normal. Kurtosis, I don't know. It's negative 0.6. It says it's pretty flat. It's because we have 2 bins. You might be able to change that if you wanted, but yeah, no concerns about the skewness or the kurtosis. It's very normally distributed. And then we cleaned it in the ultrasound, and again, very clean numbers. All of them, below 0.6, below 0.2. Also pretty normally distributed, 49% chance of it's being normally distributed. So this is, again, quick data analysis using Minitab. You can go through and analyze those things. Now, what I want to do for the rest of the time is actually walk you through doing some of these things in Excel. Okay. So I'm going to pull this over to the right. I'm going to switch this. So this, you can sit back, relax, enjoy the show. We're going to keep the PowerPoint on. I'm going to bring Excel over here. Okay, this is all of the final exam performances in PCHEM from 2004 to the present. Okay, so what we have is a departmental sort of track, because that exam doesn't change very much. Okay, and yeah, 2004 was the first year I taught here, and we'll see. I was still getting my feet under me. I wrote a really hard final exam. And so, you know, one of our tracking things is that since it's comprehensive, we want to see that our students are retaining the information, and we want the percent passing, which would be greater than 60. We want that to be, 75% or more of the students make 60 or higher. Okay, so we're looking at the percent below 60% on the final. And here's the count of all the students. So over all the years, 665 students taught in PCHEM 1. So that's pretty good. And then I just want to show you some of the uses. Here's the t-test. Remember, we did the t-test to test two different groups. And this is a t-test, the p-value that the populations are the same. And so what I'm doing is I'm comparing, say, the 2007 group to all of the people prior to it, or to the whole group. So is there anything unique about 2007? There's the 32% chance that 2007 is from the same group as all, okay? And then this next t-test is to all previous years. So this is comparing 2007 to 2004, 2005, and 2006 only, okay? So it's saying there's a 28% chance that 2007 is the same, has the same mean as 04, 05, and 06. Okay, so that's a use of the t-test. Does the spread in the students in 2007 have the same spread as all of the groups or just the previous years? That's the next two F tests. Okay, 68% chance that the behavior, the spread, and the performances in 2007 is the same as a representative or the same as the groups, either all prior years or all of the years combined. There's some that stand out. 2008, there's definitely a different mean, okay? Is a much higher group, a 97% passing, okay? And so let's look at some of the data. Now, again, these are figures of merit. These are t-test values, F-test values, means, standard deviations, but it's kind of hard to understand. It's just numbers, right? So let's go to some of the graphical methods. So looking at those numbers, you just kind of glaze over. So that's why we want to use graphical methods. Here is the box and whiskers plot for all the years, going up to 2023, so up to last fall. You can see they're all except 2004. So you picked it up right away. 2004 was unique, okay? I settled down on my exam writing, and yeah, it's been pretty much, the same performance over the years. One year or the other might be up or down, and then also it's doing the outliers. There's a few outliers in here. Well, one's a 0, that's an outlier, okay? They didn't show up. They didn't actually take the test and make a 0. So got a few hundreds up here. That 100 is an outlier compared to the performance of the group, okay? So this is, again, you have the individual data. If you zoom in on that, let's see if I can zoom in on that. Yeah. Okay. You can see the little bar there, that's the median. And these quartiles, the 25th quartile, the median is the 50% quartile, the 75th quartile, and then the range going up to the top. And then if there's any outliers, they're beyond the top whisker or below the bottom whisker. Okay. Here's a histogram. So let's just show how we do these in Excel. Let me zoom back out. So what year do you want to do a histogram for? 22. Okay. Somebody said, yeah. So we're going to grab the 22 data, Control Shift down. Okay. You remember that? Control Shift down. Okay. And then we come up to insert, recommended charts, and all charts here. We can come down here to histogram and hit OK. Boom, there it is. Okay. Now it's chosen the bins for us, but I don't really like those bins. I like the bins that have 10% increments, right? Because A's, B's, C's, that kind of thing. So I'm going to double click this x-axis, and we've got the bin. We can play around with the bins. So you get to play with your own bins and then do the thing. So bin width, it's 0.23. Well, that's kind of weird. Let's do 0.1. Okay, so these guys down here are kind of screwing things up. There's a 0 that year. There was like a 20 to 30% person. Okay, must have missed a lot of class. And again, this is not violating the Federal Education Rights and Privacy Act because you have no names. Okay, so it's just all right. This is just data. Nobody say, oh, that was me. Don't give yourself away and we're good, right? I don't think it was you. Okay, but see the overflow bins and underflow bins. So what do we want to use? We probably want to use an underflow bin at 60%, right? Because that's going to be all your F's. So let's just do an underflow bin that contains everything less than 60. So we come down here, and remember 60 is 0.6. Okay, so 0.6. There, so you see the little thing, it shows less than 60% here. Frequency, so there's 5 of those. There's 60 to 70, there's 6 of those. 70 to 80, there's 11 of those. And then 80 to 90, there's 5 of those. Is that cool? Yeah, so there's your histogram in Excel. There's other kinds of things you can go in here. You can, change the colors and all that stuff. Just all your little Excel things that you do. There's tick marks. Let's see. Yeah, so there's all kinds of features that you can change. Now, I was trying to put 2 histograms next to each other, on the same chart. I couldn't figure out how Excel could do that. So if you figure that out, great for you. This morning I was trying to compare 2 years and have an orange histogram and a blue histogram to show that in this year it was higher than that year. But Excel is not Minitab. It doesn't have a lot of the capabilities, but I'm glad they added the histogram and improved it. It didn't used to be this good. The histogram, at least for a single set of data, is not bad. Okay, here's some of the ones. This was 2020, COVID year. Here was 2018, not so good. Okay, I did a smaller box and whiskers over here, I think. No, I don't see it. Okay. Let's talk about our quartiles. Yeah, so what year was that we just did? 2022? Okay, so let's do 2022, and let's do the cumulative distribution plot and calculate our percentiles. Okay, so I'm going to do percentile for 2022. Can y'all see that? Is it too small? So I'm gonna zoom in a little bit so you can see the formula that I'm about to enter. You're gonna this hopefully will be something that really helps you. Okay, so we're gonna do a normal distribution equals norm dot dist open parenthesis. And it's nice because it tells me what it's looking for. It's looking for the X value, which is the one I'm comparing to the normal distribution. And then it wants the mean for that normal distribution and the standard deviation for that normal distribution. And then this last thing, whether it's cumulative or not. And so what we're going to do is we're going to go over and we're going to say, what is the percentile of this number here? Like in the data on a 0 to 100% range, is this the 0th percentile, meaning the lowest score, or the 100th percentile, which means the highest score, or somewhere in between? So that's what percentile means. It takes the full range of data on a scale of 100% and then gives you where that data point falls in that 100%. Okay, so that's our data point. Then we need the mean. So I'm just going to do, you can put formulas inside of formulas. So I'm going to do average, open parenthesis, and I'm going to go over there and I'm going to get the average of the whole thing. Now, how am I going to select all that data with the keyboard only? Yeah, all right. You made my day. Okay, Control Shift down. Now I want to anchor this because when I copy it down, I don't want the average to move. So I want to average the whole deal. So I'm going to anchor it. That is with what function key? F4. Yeah, okay. I don't know what you said, but it's F4. All right, then the standard deviation. We have more than 15 points. And so let's go ahead and use the population. So STDEVP, okay? So STDEV dot P, open parentheses. And so I'm going to go over, Control Shift down. You gotta have sound effects. And F4. All right, so we've got those, close parentheses. So now I've got the average of that data series. I've got the standard deviation of that data series, and I'm seeing where does that X value fall within those guys. And then this is the thing. We want a cumulative distribution, and I'll show you both of them, but this is the cumulative distribution, which goes like an S curve. Okay, so we'll show you this. So I'm going to say true. Sounds kind of funny, but that's what you put into the formula, true. And that gives us the cumulative distribution, and then you hit enter. So this data point, this score, 66% on that final, is the 46th percentile. Okay. You know, if you took the SAT or whatever, you know, you got your percentile score. This is how it was calculated. So I'm just going to take that formula, double click the little cross in the corner, and I get them for everybody. Okay. Now here's that 0. Obviously, the 0 is the 0th percentile. Okay. All right. Now let's plot the percentile versus the grade on the test. Don't be confused by what I do right now. Okay. I'm going to plot 2023 by 2022, but then I'm going to drag that column over to the percentile after the plot's made. Okay, this is my shortcut. So I'm just this seems weird. I'm gonna plot these two columns. Okay, insert XY scatter. Oh, wait a second. Hold on. Okay, it went. Oh, I need to delete these points here. It went all the way down to like column A or something like that. Okay, so we're just going to plot all three of these columns, and I'll delete the 2023. All right, so we come over here to XY scatter. We want to plot the data points only, okay? Because if we plot with the crisscross, look at what it does. Right? It's connecting all of those. So we just want the data points only. Okay, so there's our chart. And one of those is the 2023. We're going to delete that because it's not the percentile. Yeah, so there's our S curve. What is going on? Okay. So do you see the S curve? It's coming along here, and it snakes up, and it goes up to 100%. This x-axis, delete that. We'll do chart axes here, our axis titles. Okay, so this is percentile. Yeah, that's good. And then this is final exam grade. I wish I had some lines that went down and connected the data point to the x-axis, right? That would be really convenient. So I could look at the data point and then see how it comes down. So this is nice. You can come along here and you can do error bars, okay? And I want to click on those guys. I don't want the horizontal error bars, so I'm going to click on those and hit delete. And then on the lower error bars, I want to format those lower error bars. So how do I do that? Well, once I've selected them, you can come up here to do format and format selection. So whatever you have selected, now you can format it. And I don't want both. I want minus only. So I want the minus only. And I want it to go all the way to the bottom. No matter what the data point is, how do I get all the way to the bottom? I subtract 100%. So the error amount, I want to go down 100%. And it goes all the way to the bottom. So that's kind of cool. And so now I can see on this y-axis, let's go here and set our major units as 0.25. And those are your quartiles. When we talk about the 25th percentile, the 50th percentile, the 75th percentile, and the 100th percentile, that's taking the full range of 100% and dividing it into quarters. So the 25th percentile is coming over here. It's hitting close to that data point. So that would be around 55. So grades below 55 are in the lower quartile. Between 55 and wherever this 50% mark is, so 65% roughly, 55 to 65 are in that middle lower quartile. It's the 25th to 50th percent quartile. What's the average for my exam scores? That's the 50th percentile. It comes along, hits that, comes down. So this average was around 70. Let's make this, it's these units right here. Let's do 0.1. It's going to be busy, but there it is. All right. So yeah, the 50th percentile comes along and hits just below 70. Kind of a tough year that year. 75th percentile comes up here and is around 80. Okay. If I wanted to force this into a bell curve, you know, where I had 10% A's and 20% B's and whatever, you could do the percentile ranks at 10% increments, and you could say anybody in the 90th percentile gets the A, between the 70th and the 90th gets a B, and so on. And so that's a nice objective way to assign grades, and that's what I do typically. Although I don't curve down. Like let's say the average was an 80, I'm not going to make that a C. Okay. So, but if the average was 65, that's average performance. That's going to be a C. And so I will use this to curve up, but I won't use this to curve down. When you do a box and whiskers plot, I can't really mark on this with my pen, but the box is the 75th to 25th percentile. So all of these data points right here would be in the box. And then the whisker would go up to this one. Let me see if I can just grab that chart, copy it, dump it into the PowerPoint. Let's see. Okay. Yeah. It worked. Okay. Let's see. Undo. Let's do. Thank you for bearing with me. I know this can take a little while. Let me go back to the PowerPoint. And let's close this out. Yeah, okay, we're good. That's the PowerPoint right there. All right, so this is the box and whiskers plot. If I were to do a box and whiskers plot, this 25th percentile would grab that data point, and the 75th percentile would grab this data point. So my box would be right here. So this would be my box. And my top whisker would go up to this point right here. The median would be the middle data point. So this might be the median right there. And then my lower whisker would probably go down to here, and this would be an outlier. So that's how the box and whisker plot is made behind the scenes. It calculates these percentiles. It draws a box from the 25th to the 75th percentile, and it contains all those data points. And so then that's, you know, that's what's shown in terms of the box. And then you have the whiskers that go to top point, the bottom point, if there's outliers, it's typically shown as a data point or some sort of asterisk. Any questions on all of this? Seriously. Okay. Can we determine if this data is skewed just by looking at it? Don't be confused by the S curve that makes it look skewed, but try to look at where the density of the data is. You know, if we did a histogram at five point bins, let me just erase my whisker here, box of whisker here. Okay, so every 5% we did a bin. And then the 60 would be these 5 right here. You know, we would have a square or a bin or a frequency of 2 there. We'd have 3 here. We'd have looks like a bunch right here. This part for that 5% bin would be about that big. Then back down to 2. Maybe 1 or 2 there and 1 here. And then the catch-all for 60 will be up around 5. But it does look like it's skewed left, negative skew towards lower numbers, right? Because you've got a bunch of data here and then it tails out. So you could look at the data and say it's skewed low. Okay. Well, if there are no further questions, then enjoy your day.